All right, good day, everyone. We're going to be talking about the next lesson, which is geometric sequences. And in this lesson, we're going to be talking about, instead of a finite, an infinite geometric sequence. Okay, we're going to kind of discuss what does that really mean, how does that represent, and then how do I actually solve it out if I have any type of sequence or series without a bound. Okay, so let's go ahead and get right into it. So a couple of prerequisites that we need in the past lessons we won't need to talk about. We're still continuing dealing with that triangle lesson in which a of 1 was 8 and our ratio was square root of 3 over 2. Okay, so that was kind of the first concept that we need. We need to know those two pieces of information if we want to continue on. Okay, and so for the question for the first one here, as n increases, what is happening to the length of each successive hypotenuse in the triangles? Okay, in Shelly design. Well, n is basically the number of triangles we want, right? That's the term number. That's the fourth, the fifth, the sixth triangle. So basically what we want to try to understand is, as our exponent goes up in our equation, a of 1 times r to the n minus 1, okay? So when our exponent n continues to increase, what actually happens to our answer? And if you remember back to the actual problem itself, what happens is your answer ends up decreasing. So it decreases, okay? And that's an important concept to understand. Even though that we're going into the next triangle, we're going up in our triangles, our answers are actually decreasing each time, okay? This is where the first important piece of information kind of comes into play. In terms of an infinite sequence, which basically means that we have a sequence that doesn't end, okay? In terms of an infinite sequence, approach some number L as n increases without bound, the sequence is said to converge. If the sequence does not converge, it diverges. Okay, so we have two specific words that we have to understand and kind of go into detail. We have converge and diverge. Okay. Basically, the way to understand this is that if something diverges, its goal, or basically the series or the sum of that sequence, continues to go on to infinity. Okay, there's really no end to it. It's not going to reach a specific value. It's going to continue on. Okay, a converge however, does not do that. It's not going to settle at, or it's not going to keep going into infinity. It's going to settle at a specific value. Okay, a converge at some point has a value of which with it, or which a value that goes with it, I should say. So let's look at different sequences and try to be able to tell which one does which. Okay. So if I look at number 3 here, for each infinite geometric sequence below, answer the following questions. Determine the common ratio for each sequence, and then determine whether it converges or diverges. Okay. So this is the big thing we have to understand. For the first one, in number 1 here, we have 0.025, 0.25, 2.5, and 25, 250. Okay. Now the easy way to determine how to figure out the ratio is to take a value and divide it by the previous. So I could take 0.25 and divide it by the previous term, which is 0.025, and that would give me an answer of 10. So we know the ratio equals 10. The next piece of information that we want to try to discuss is, how does this affect the problem? Well, if I'm thinking about this problem in general, notice how as I go along here, the values keep increasing and increasing and increasing. If I continue on that ratio, there's really no end in sight, right? It's going to be 2,500, then it's going to be 25,000, then it's going to be 250,000, because all I'm doing is multiplying by 10 each time. So because of that, there's really no end in sight. It's going to continue to get bigger and bigger and bigger until you get to this infinity number that we can't even count to. So what this does is it diverges. Okay, that pattern continues on to a point where you cannot solve for a specific answer. Okay, for the second one, now we start looking into a different pattern. Okay, 100, 50, 25, 12.25, 6.25. Now I could use my equation to solve for the ratio, but hopefully for this one we kind of see it, and that the ratio is going to be 1/2 or 0.5. Okay, I'm multiplying by a half each time. Well, in this problem, it's a little bit different. Okay, in this problem, we actually converge. And here's the difference why. Here's why we actually see this one. In number 2, notice how the values are always getting smaller. If I continue this pattern on, and on and on and on, eventually that value is going to be so insignificantly low that it's really not going to change any sort of sum of that pattern. It's going to continue on forever. So in this case, it converges to 0. Because eventually your value in this sequence or the term number is going to be so low to where we're basically can just assume that, okay, this is a 0. This is a 0 value. So that's kind of the big difference between the two as we see. A diverge is going to continue. It's never going to settle at a specific location versus a converge, it's going to actually settle at a value. Eventually those values are going to be so insignificant that we're going to be able to sit and stay at that specific value itself. And so I can pretty much do that down the line here. Now, number 3 is kind of a tricky one because if you really look at this, your ratio is just -1. You're multiplying by -1 each time. Now, for a lot of people might look at this and say, like, well, it converges, right? Unfortunately, this one doesn't. This one actually diverges. And this is kind of one of the different ones in which I always said diverge, think of infinity. In this case, yes, it's not going to get bigger or smaller, but you don't really reach any sort of particular pattern. Okay, you just flip-flop back and forth. Because of that, you can't really converge to a specific value. There's no specific value to converge to. Because of that, it's going to diverge. Okay? Same thing here. For number 4, our ratio is -3. And because of this, not only is it increasing, but because it flip-flops between positive to negative, that one's also going to diverge. So we kind of have this idea, right, of what are some things doing? How is it actually growing? How is it getting bigger? How is it getting smaller? Okay. A diverge sequence is going to continue or have no set value that it reaches versus a converge sequence is going to actually have a value that it reaches. Okay. So now what we want to do is try to think, okay, like how could I base this off in the equation? Okay. So if I go to I want to actually go back to number 4 here. We want to create 2 sequences that actually are going to allow me to create a converge or diverge sequence. And here's the main thing I want you to think about. We're going to use the equation A1 times R n minus 1. Okay? And so what we're going to do then is try to think, okay, well, how can I actually come up with a converge or diverge statement based off that equation? Okay? Well, here's how we have to see this. A of 1 is your first term. So that's not really going to change things that much. So let's just say we can create an A of 1 equal to 2. Now, the big thing that's going to cause differences in this problem is your ratio. And we're going to play around with that ratio. Okay? If we go back to the last situation, we talked about how a ratio is really a growth or decay function. Okay? Your ratio really determines whether you increase or decrease in any sort of pattern. For example, if you really think about this, if you have a ratio of 2, you're going to continuously grow because you're multiplying by 2 each time. No matter where you start at, you're always multiplying by 2. Versus if I had an A of 1 of 2 and then a ratio of 0.5, we note that that technically should decay. I should be getting lower and lower and lower, right? So if I were to actually write these equations out, this would be 2 times 2 to the n minus 1. And this one would be 2 times 0.5 to the n minus 1. Now, the key thing I want you to see is what do these values affect, or how does it actually change our problem? Well, the thing is because this number is greater than 1, automatically I can assume that this is going to be a diverge statement. Okay? And the whole idea is that if that value is bigger than 1, automatically, because I'm multiplying by 2 each time, it has to grow. Versus this problem, this has to be a converge. Okay, and the whole idea with this one is that you have a value or a ratio that is less than 1. Okay? And because of that, no matter what, every single time I'm multiplying by 0.5, which naturally is going to make my value go down. And so we can basically make an assumption about these problems. if the absolute value of R is less than 1, and I put absolute value in there because we can't have a negative ratio, okay? I put an absolute value because I'm not allowed to have a negative ratio. Then automatically I can basically assume that this is a converged statement. And this one's going to converge to 0. If I have a ratio equal to 1, this is going to also be a converged statement. We don't really see this one too often, but it's going to actually converge to your first term. And then last but not least, if I have a ratio greater than 1, this is when it actually diverges. And if something diverges, there's no particular point that it actually works to. Okay? So notice how I can pretty much determine whether something's going to converge or diverge based on what the ratio is actually equal to. Now, with that being said, let's kind of talk about how this actually affects with an infinite sequence or series. Okay, let's actually talk about how this actually goes into depth. On number 10 here, we're actually looking at an infinite sequence and an infinite series. An infinite sequence is a sequence with an infinite number of terms. Okay? A lot of times if you see something like an infinite sequence, you'll see like 2, 3, or hold on, let me actually do something that's multiplying. Excuse me. 2, 4, 8, 16, ... Okay? What these values represent right here, these ... is that this is going to continue on forever. There's really no ending point. This here is an example of an infinite sequence. Now, an infinite series would be the same thing, but all I would do is I would take those same values and then just add them up, right? Same concept, that is an infinite sequence. So what we want to try to understand is, how do we actually solve to find a value or a sum in an infinite series? Okay? Well, to do this, we have to kind of understand. To this, we have to kind of understand, like, what are we given, what's actually happening, okay? So they give us this prompt right here. Basically, we have our series equation, and they're telling us that the ratio is less than 1, which, once again, remember, if the ratio is less than 1, automatically I can assume it's going to converge to 0, okay? So I want to basically say, okay, well, why does this make sense? Well, if I have R of n, what I can automatically assume is that this is going to converge to 0, right? Because my ratio is less than 1, as stated up at the top. And based off of our information, if our ratio is less than 1, it's going to get closer and closer to 0. Okay? So now, in letter B, I'm basically saying, if this gets closer to 0, well then, basically, can I pretty much assume that this is just going to be 1 minus 0 at one point? Right? Because this is directly related back to this portion. So I can assume here is that this equation converges to 1, right? Because 1 minus 0 would give me 1. So then, in the last portion, your letter C, let's apply both of these values. Let's kind of understand how both of these work, right? Well, R of n is going to converge to 0. So, in this second portion, if this is going to converge to just 1, this 1 minus R of n, I can pretty much rewrite this in the fact that if I have an infinite sequence and I want to find the series of it, I just need to take A of 1, because that first portion up top here, okay, this portion, let me get a different color here, this portion approaches 1, so I can pretty much assume A of 1 times 1 is just going to stay the same, divided by 1 minus R is going to give me an infinite sequence. Okay? This would be the series of an infinite sequence. Okay, this is giving me the sum of an infinite sequence. So let's kind of talk about how we can apply that. In number 11 here, we go back to that triangle problem. Shelley wants to know the total length of material she will need for the display. Find the sum of the length of the hypotenuse in the triangles in her design of A of 1 and the number of triangles in her design, and the number of her triangles in her design increases without bound. Key term here, without bound. Automatically, that's like saying this is an infinite series or sequence, because I'm basically telling you that there is no limit to the amount of triangles that Shelly can create. Well, now this is an important concept. I got to figure out, well, if I want to add every single possible triangle together, what would be the lengths of all the hypotenuses put together? So we know we have to use the equation of infinites, which is the series equals a of 1 divided by 1 minus r. We already know the first hypotenuse length is 8. We already know the ratio, and this goes back to that very first lesson, the square root of 3 over 2. So now all we have to do is solve this out. To find the infinite series of all those triangles, I have to take 8 divided by 1 minus square root of 3 over 2. And if I do that, I get a total hypotenuse length of 59.713 feet. Okay? And this represents the sum of all possible hypotenuse lengths. Okay? So in past lessons, we'd always find a partial sum. Okay, I'd always say, what's the first 8 triangles, the first 10 triangles? In this lesson, what the infinite series does is it does all possible. Because even though there's really no ending of these triangles, you could keep going on forever, at some point, the hypotenuse length is going to be so insignificant that it's not going to affect your final answer here. So we can basically assume that this would be the sum of all the hypotenuses put together. Okay? Thanks for watching today's lesson. Make sure you answer your questions on the Edpuzzle. Besides that, hopefully this worked out for you. If you have any questions, bring them to class, and you have a great day.